So welcome everybody to a new session of now Lógicos with Saindo da Quarentena. It's a pleasure to receive Professor Edson Bezerra. Edson, thank you very much for accepting our invitation to begin this new season. Thank you.
Thank you, Bruno, for the invitation, and thank you for attending this seminar. I will present in this talk a certain development from what I did in my PhD thesis. There I investigated some concepts which can be formalized into modal languages, and then I had to deal with a certain family of modal logics. And then, for the sake of generality, I also investigated the non-classical counterpart. So I present there this non-classical counterpart. These logics I investigated are the many valued counterparts of Lemmon modal logic S0.5. In his original paper, the logic S0.5 is intended to capture the concept of tautology. So box phi means phi is a tautology by the truth table method. Okay. Since I am studying a family of many valued logics, I call the logic L S0.5. This L is a propositional modal many valued logic. Okay. These logics were investigated in a paper which I published with my PhD supervisor, George Venturi. But in this paper, we worked only in a semantic perspective. Okay, we presented the models. In the appendix, we presented the axiomatization of the three-valued Lukashevich logic with these modalities. But it was the only logic we investigated in a syntactic perspective. The others, we analyzed only the semantic side. Okay. I will present a characterization results for these logics, and then I show how to strengthen the results for stronger modal systems. Also, many valued counterparts of normal modal logics. Okay. So we begin by the traditional definitions of modal logics. Propositional logics. We defined any valued logic L with the language L. I put the subscript here because some logics have implication, the others have negation, implication, conjunction. So I presented here in a very general way. Okay, the language has a countable set of propositional variables, and we have connectives of RTK. Okay. And then the set of formulas is defined as usual. The matrix is a structure with we have a set where we have a set of truth values, a set of operations, and a subset of the set Vn, which we call the set of designated values. Here I adopted the traditional notation of rational numbers, where 1 denotes true and 0 falsity, and then the intermediate values are the non-classical values. Okay. The evaluation for L is a homomorphism, which can be extended to the whole set of formulas in the traditional way. Okay, and then notions of model, tautology, and consequence are defined as usual. Tautology is the uniformity of designated values for every evaluation. The logical consequence is the preservation of designated values from the premises to the conclusion. Okay. So here I put a restriction in the analysis because we are working with many valued logics which are fragments of classical propositional logic. So we put this constraint, the constraint of normality. This definition appears in Nicholas Rescher in his book of many-valued logics, and in 1969. Any valued connective C is called normal with respect to the matrix M if O, if its corresponding interpretation, the operation O in the matrix agrees with classical logics when we have the classical truth values. Okay, so if we erase all the intermediate values, we obtain classical propositional logic. So a logic L is normal if the connectives are normal. So in this analysis, I don't include, for example, some presentations of connexive logics. As far as I remember, there are some presentations of connexive logics where the non-classical we have a non-classical value with classical values are arguments. Okay. So based on these logics and this restriction, I introduced the many-valued logics, modal logics L S0.5, which are, as I said, the many-valued counterparts of Lemmon modal system S0.5. Can I proceed or any question?
You may proceed. You may leave the questions for the end, maybe, or if you have any important point.
Okay. So the modal logics that we will consider here contains two modal operators, box and 5. They are introduced as primitive in the language. So the modal semantics for these logics are defined as follows. We have the matrix for the many-valued logics, for the many-valued logic L, and then we define the modal model of this many-valued logic L S0.5. Well, so these modal structures have a set of words, a subset of W of normal words, an accessibility relation defined only for normal words, in the sense that every normal words see the other words, but the non-normal words, we don't define, the accessibility relations for the non-normal words, okay? We can find, for example, this definition in the Graham Priest book about on non-classical logics. He defines the semantics for many non-normal modal logics, and the logic S0.5 can be defined semantically defined in this structure when we have the set of words and the subset of normal words. Okay, and we defined an assignment for any word, which can be recursively extended in the same way as the propositional case, and the modalities are defined in this way. For normal words, we have that box phi is true in the normal word W if phi is designated in all words accessible to W. Otherwise, it is false. And then the diamond, we have diamond phi is true if at least in some word phi is designated. Otherwise, it is 0. When W is non-normal, the values are arbitrary in the set of truth values. Okay. So the notion of true is defined only for normal words, and validity formula is also defined only for normal words. Okay. Note that the definition, even if the modal logic is many-valued, the modalities give only classical values to the formulas in the normal words. Okay. So, because they are bivalent, the biconditionals, box phi, if and only if, not diamond, not phi, and diamond phi, if and only if, not box, not phi, are not valid anymore. Okay, so they were introduced as primitive because such biconditionals are not valid anymore. Okay, you can't define in these many-valued logics diamond in terms of box and box in terms of diamond. Okay, and then in this paper with Giorgio, we proved that these logics capture the notions of tautological validity and logical consistency of the many-valued logic else. Okay, because we are considering a wide family of logics, many modal principles are not valid. For example, the axiom K is not valid when the many-valued logic is the logic of paradox. The necessitation rule is not valid when we consider strong clean logic. So many of these modal principles are not valid in general. Okay, but every modal logic LS0.5 validates these schemas. First is the version of axiom D. We have the inferential form of axiom T. We have the dual, in some sense, of the axiom T, and then we have this version of modus ponens for boxed formulas, and the introduction rule defined in terms of tautological consequence. Okay, so whenever psi is a tautological consequence of phi, we can introduce the box in phi and in psi. So these logics also have the characteristic that they do not validate interrated modalities. So we cannot have formulas with box, 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 box phi, or diamond, diamond, diamond phi, or their combination. Okay, because the truth of boxed formulas is defined only in normal words. Now, some questions?
Yes, Edson, just to clear, it's not possible to have nested modalities in any case?
No.
Okay.
No, we can, for example, in the classical case, you can prove that S0.5 is equivalent to the modal logic T when the formulas of T are of the modal degree 1.
Okay, I understand.
So we do not have nested modalities in this logic here because of this partition of normal words and non-normal words. Okay.
Is it a cost? Okay. Let's go ahead.
No, you can ask, no problem.
Just try to understand why.
Because the main reason was to preserve the intended interpretation of tautologicity. For example, if phi is a tautology, then box phi is true. But box phi is not a tautology anymore, so you cannot apply the box.
Okay.
It is just to preserve the intended interpretation.
That's really a project decision.
Yes. Can I continue?
Sure.
Okay. Now I will present the proof systems for these logics. So, but Here, I will present Tableau proof systems. As one knows, Tableau for many-valued modal logics are not new in the literature. For example, we have Graham Priest paper where he presents label two-signed Tableau systems for the many-valued logics, many-valued modal logics based on the logic of paradox, the logic of strong clean logic, and the first-degree entailment. He presents these tableaus in his book and in the paper, which is basically the chapter of the book. We could, in principle, apply his method to our logics, but his two-signed tableaus face a problem when we have more than three truth values. For example, now I will give, in the propositional case, the tableaus for strong clean logic. So I will explain why we cannot, at least directly, take his method and apply to the many-valued modal logics I am working. So strong clean logic has these matrices, negation and conjunction. One is the only designated value, and we can present the Tableau system for strong clean is defined as follows. We have the two labels, plus and minus. We can put in the place of plus the label true with T and the minus the false with the F. Okay, we have these rules here for conjunction with plus, conjunction with minus, negation of conjunction with the two labels, and the double negation. So he defined a branch closes, a branch B closes if it contains formulas, if it contains, signed formulas, box phi plus and phi and neg phi plus. Okay, so a branch closes whenever we have phi and not phi, and both are plus, designated in a higher perspective. Okay. Here I do not present the basic definitions of his tableaus. I just presented the rules and the definition of closure. Okay, but the problem is when we take this procedure of two-signed tableaus and apply to the other many-valued logics, we have the following problem. Not every logic has expressive power enough to distinguish their intermediate values. In the case of strong clean, we have, because whenever we have in a branch phi minus and neg phi minus, we know that the value of phi is 1/2 by the adequacy results of strong clean. But if we have more than 3, the negation alone, along with the labels plus and minus, may not be enough to distinguish the intermediate values. The example is simple. Consider a four-valued logic which has two non-designated intermediate values, I and I prime, such that the negation of I is I primus, and the negation of I plus I prime is I. Okay? For example, if you take the family of Lukashevich logics and the family of clean logics, if we consider the four-valued logic of clean and the four-valued logic of Lukashevich, we face this problem. Okay, you cannot distinguish the intermediate values in terms of negation. This difficulty can be a problem if we want to provide a Tableau system for these logics. We can solve this difficulty by extending these logics with connectives capable to distinguish the intermediate values, or we can define an operator inside the logic which allows to distinguish those values. But in this later option, we depend on the expressive capability of the language. In the former, we can extend the system if we want to maintain the these two labels. Here, I adopt a perspective proposed by Carnielli in his doctoral thesis, where he provides the label tableaux for many valued logics. But here I extend his procedure to many valued modal logics. Okay. His Tableau system has the advantage of being user-friendly, in the sense that they are easier to manage, even though it has more labels, but it is easier to compute the inferences. Okay, and the other advantage of his procedure is that we can, for example, extend these tableaux to non-deterministic semantics, as as Pavlovsky done in his paper, where in his paper he proposed an extension of Carnielli Tableau, and then he formalized a system, a non-deterministic system, and he used this label Tableau. Okay. For simplicity, I adopt the following abbreviation. For any truth value m, n-1, I denote it by tm. Okay. It's just to facilitate the reading. So when we have t0, we are abbreviating the value 0. When we have t n-1, we are talking about the value true. Okay, this is to facilitate the reading when we consider the labels of the Tableau. Okay, so let's jump to the definitions. Now we define the notion of signed formula. We have, if let be phi a formula and tm a label. For every tm belonging to the set of truth values. Sorry, here is the set of truth values, not the set of propositional variables. So we define a signed formula in this way. Here, tm phi comma I. So the I here will denote the possible words. Okay. So we construct the Tableau given a signed formula and this natural number I. We can construct a tree, for this signed formula as follows. Phi is the initial node of the tree. We will expand this root by applying the corresponding rules for this labeled formula, decided formula, and every branch B contains a signed formula resulting from the application of the corresponding rule, of its corresponding rule, and possibly these two numbers related by the relation R, which is a rule between natural numbers, whenever phi is a modal formula. And the endpoints of the tree are the nodes which contains formulas for which there is no rule to be applied. Further, I will show that some endpoints can be inhabited by modal formulas. I will, when I present a concrete example of a system, I will explain why this happens. So we can extend these definitions for set of formulas in the obvious way. Now, we define the notion of complete branch. A branch is complete if every rule which can be applied is in fact applied, and the tableau T is complete if its branches are complete. Now, the definition of closure is, we say that a branch closes whenever if there is a formula phi which has different labels occurring, of course, in the branch B, or if any question?
Yes. Is it not possible that some formula can be applied more than once?
If you have
every formula in the Tableau, every node can be applied only once?
If you have, whenever you apply the rule, you expand the branches.
Yes, but some rule can be applied twice?
Well, yes.
Because so if you have a branch that is complete, but it's also possible to apply rules in this branch that is also complete. I'm just trying to understand the definition.
Okay. You have
rules you can apply more than once. Or no?
So let me see that. No. Sorry. Whenever you apply the rule, because this rule will decompose in many cases.
Mm-hmm.
So it's not.
I'm sorry to make a question in the wrong time. We may discuss it in the end, if you prefer.
Okay, I will present an example, and then you'll see if it will be clearer. Okay. In the next slide, I will present a concrete example of these tableaus. Okay, now I will present the rules of Boolean connectives. Okay, here we have this general rule of for propositional connectives. Then the notations of this big V and this big OR and the big AND mean that we are expanding. We expand into the formula into the different branches, and the big AND is the expansion into a single branch. Okay, and V is a homomorphism of the matrix into the language, from the language of L to the matrix of the many-valued logic. Okay, this is here. Until here, we have only the definition for the propositional logics. Now we expand to the modal case. We have the first definition of box. So here we have T n -1, which means basically truth. So the application of this rule, you expand in many cases, possibly the formula into many branches, and these branches, the labels denotes the designated values. Okay. The rule of falsity, when T0, basically T0, the truth value is 0. So we expand into branches whenever phi receives a non-designated value, okay? And the same reasoning applies to the diamond, okay? And the rule R is the rule of reflexivity, okay? The rule we call here the rule Ho, okay? So is the rule of reflexivity. So the definition of proof, we have that sigma, this set of formula sigma proves phi if every tableaux T satisfying these four conditions close. So for every premise, we have the signed formula with a designated value. The modal formulas receive only T n minus 1, that is 1. And conclusions receive here non-designated value in the label. So a Tableau closes, the relation of probabilities defined with these four clauses. Now we give a complete example. We take the propositional three-valued modal Lukashevich logic, which is characterized by the structure which I presented before. The connectives, the true functional connectives are the negation and implication. The matrix has three values, and just one is the designated values. And the matrix are defined as follows. The truth tables, are defined as follows. Negation maintains the intermediate values independent of the main applications you give. And the implication is defined by this truth table. So based on these the rules I presented before, we have these rules here. For negation, we have when not phi has the 1 with the label, we have 0. So negation if the intermediate value preserves the same value. Negation of the label when it's false, we have a true formula. The box expand only to a single branch because 1 is the only designated value. The diamond expand expands the branch with E, where E is new. And the falsity of box is similar to the definition of diamond, but here we have the falsity. And the falsity of diamond is defined analogously to the case of box, but here we have the falsity. But now we expand in two branches, where in the first branch we have phi receives the label 0, and in the second it receives the value, the intermediate value phi. Okay. The implication rule when 1 is true, when phi implies psi receives 1 as a label, we expand the rule with 6 branches. In this case, when phi and psi receives 1, when psi is 1 and phi 0, 1.5, when both have the intermediate values, and so on. So in the case of the intermediate value is a label, we expand in these 2 branches, and when it is 0, we have only 1 branch. Okay, so as an example of how to prove in this system, consider this following formula. here. So we have two tableaux for this formula, and both close. So since both close, then we have that this formula is in fact a theorem of the system. Now, Bruno, I don't know if this example helps.
Yes, it helped, but is it possible to apply the rule and have something different than the zero on the right, or no?
Okay. Zero is in the right side.
Yes.
Yes. Sorry, it was
at this point you can apply the rule more than once, right?
When you have, for example, zero here, but if you have now we have the label zero, but we can correct it was E instead of zero. It was a mistake. My mistake here was
okay.
Zero, the formula, and the natural number, the E is not E, not zero. In the right side of the comma.
Okay, it's okay. Thank you.
So these tableaus have the disadvantage of being very big when we have, depending on the set of truth values you have. Okay. In the case of Lukashevich logics, it's simple because we have only two non-designated values. But when we have, for example, 3, 4, 5 non-designated values, the verification is very big. It's very long.
Okay.
As I said before, some nodes may have other formulas than atomic ones. Suppose, for example, if a branch which contains this formula and this label here, okay? Suppose that box not box P implies box not P in the word zero, okay? Applying the rule applying the modal rule, we obtain, for example, we pass to the word 1. So in the word 1, this formula is true. Applying the negation, we have 0. We have that the box P implies box not P is false. And applying the rule of falsity, we have box P and box not P. But this branch do not close because we cannot apply the rule for box here, because as I defined it before, we can apply the box rule only in the word 0. Okay, in the words bigger than 0, you cannot apply the rule anymore. So since there is no rule to be applied in this case, the verification stops, and this branch here, for example, remains open. Okay, so some endpoints of the tableaus for Lukashevich logics extended to the modal Lukashevich logics may contain formulas other than the atomic ones in the endpoints. Okay. In a wider sense, we cannot say that these tableaus are analytic. Okay, because we cannot decompose these tableaus to propositional variables in general because of these examples like this. Now, the characterization results of these tableaus are quite simple. We define the notion of faithfulness. For example, we have that a model is faithful to a branch if and only if there is a mapping from the natural numbers to the set of words. Here we put that 0 is the normal word, and the other natural numbers denote non-normal words, okay? So we have to put now a restriction to the words bigger than 0. That is, if box phi in the word E receives the label Tm, so the value of this formula is Tn, okay? And for every node, if phi in the word E receives the label Tm, then the evaluation with the function gives the value Tm. By giving a proof where we check case by case, rule by rule, we can prove the following lemma: let T be a branch and M a model. If M is faithful to the branch and a rule is applied to it, then it produces at least one extension B prime such that the model is also faithful to the branch, the extended branch. Proving this lemma, we have the soundness result. And for completeness, we define the notion of interpretation induced by the branch. Okay, the interpretation, the model M is induced by the branch B. We define this interpretation as follows: the set of words is the set of all words which occurs in the branch. We define the accessibility relation in this way here, and we define the case for atomic formulas, okay? And we also put the restriction we put in the case of soundness, in the definition of faithfulness, sorry, okay? Now, in this case, by induction of complexity of formulas, we can prove this lemma, and then we have the completeness. Well, these tableaus, these logics in general, are very weak. As I said before, in the classical case, we have, for example, that you can prove that S0.5 is the fragment of the modal logic T whenever you consider formulas with modal degree 1. But we can strengthen these systems and obtain stronger modal systems, many valued modal systems, okay? Now I present the logics LS5, which are compatible with a stronger validity interpretation. This validity interpretation is not the probability interpretation. It's it's more general, I should say, because the logic S5, for example, is not compatible with the mathematical probability interpretation. The logic of probability of Peano arithmetic, for example, is the logic GL. They are incompatible. But S5 captures some interesting notions of validity, and then you can extend this result for many valued logics in general. The semantics for these many valued counterparts of S5 is defined easily defined. We consider here now a standard model where we do not have anymore the set of normal words, because here now, in fact, all the words here are normal. So we have the set of normal words, which is the set W, the accessibility relation defined as usual, but R here is an equivalence relation. The valuation V is an assignment and can be recursively extended, defined as follows. The Boolean cases we already defined. Now the box and the diamond are defined for all words. So box phi receives 1 in the row W if phi is designated in all words accessible to W. Okay, the similar definition happens with the diamond formula. Okay, if at least one word, in one word, phi is designated, on the contrary, it is false. Truth and validity now are defined for all words in the model. So it is basically the definition of normal cryptic semantics applied to the many valued counterparts, okay? But even in these logics, the biconditionals of these modalities do not hold, because the bivalence of the modalities breaks the validity of these biconditionals, okay? So both must be taken as primitive in the language, okay? Now, beside the principles we presented before for those logics, we have the inferential version of transitivity and the inferential version of the axiom, the axiom 5, okay? And then we also have here a more general notion, introduction rule. Yeah, if psi is a logical consequence, not a tautological consequence anymore, is just logical consequence of phi, then we can apply the box to the premises and into the conclusion. Okay. The tableaux for these logics are defined similarly as the previous case, but here the notion of closure is applied to it's more general. We cannot we do not need to preoccupate only to this subset of normal words we presented before. Now, the notions of the rules for box and diamond are now holds for all words, not only for 0. Okay, so now we regain the possibility that all endpoints are atomic formulas, because we can apply the necessitation rule in all words. Okay, and the rules and the accessibility rule now obeys the rule of transitivity and the rule of symmetry. Okay. And the notion of faithfulness is quite the same of the previous case, but now we do not need to make restrictions in the behavior of modal formulas in non-normal words, because we do not have non-normal words here. And then we can prove the soundness. We can apply now the definition of interpretation induced by a branch in a similar way, but here all the words are normal. And then we prove the lemma, the key lemma, and then we prove the completeness. Okay. Now, you can object me by saying, well, Edson, the tableaux you presented to us are too semantic. I recognize this objection, and the further step of this research is to develop alternative proof system for these logics. We do not have these semantic, which are not too semantic, to say better. Okay, so we intend to, in the future, to generalized the sequence calculus provided by Baz and Richard Zach, where they have what we call today the n-side sequence. And in this sequence, I think that it's possible to provide the proof system I want for these logics. And second, I want to explore the probability interpretation of these many-valued logics, okay? To compare, for example, if the probability logic of Peano arithmetic of Lukashev's logic can be formalized as the L3 version of KGL, for example. Okay, so thank you for watching, and sorry for the English. Okay, thank you.
Thank you very much, Edson. So we have some time now for questions from the audience. John?
I have one question. If first of all, thanks for the talk. If you can put in the slide 30, just to make clear the difference between. So the only difference between the logic L as 0.5 and this logic is that in this logic, W and N coincide, right?
Yes.
But in the case of L as 0.5, can W and N coincide?
In certain cases, yes, it can coincide, but in general, no.
Okay, I was just wondering about this notion of strongerness, because in this case, in my viewpoint, so if L as 0.5, if in L as 0.5, N and W can be the same, so everything you have in this system you have in this LS5, right?
Yes, but S5 in this case, the accessibility relation is stronger. In the former case, the reflexivity, we have only reflexivity and only for normal words. So if W and N coincide, we have in that case the many-valued counterpart of the logic T.
Okay.
If, for example, if you say, if I defined the accessibility relation in the former logics L as 0.5, if I put the transitivity constraint, it would not make difference into the set of validity formulas, because there are cases when W and N are equal, but the other case they are different. So the transitivity constraint would not help in increasing the set of valid formulas. You understand?
Sure. Thanks.
Thank you.
Any other question? So maybe a silly question. You showed that some equivalency reactions of S5, but in these axioms you have nested modalities. So how do you prove it?
In the case of?
No, just when you show some axioms of S5 that holds in the logic. Yeah.
Yes.
Now you have nested modalities.
Yes.
So how can you show this equivalence?
Because in this case, no, the biconditionals are not equivalent. The biconditional box and diamond, they are not equivalent, but we have now nested modalities. Yes.
Yes. My question is just about the two relations that you show.
For example, when we have box phi is true, it's true in every word. It's designated in every word. Okay.
Okay.
But in this case here, since all of the words are normal, you can apply the nested.
Okay, I got it.
If you apply, okay, you can you regain, for example, the rule of we can apply the rule of box in all words. If, for example, I present into axiomatic version, for example, take the Lukashevich logics based on S5, okay? We in this case, we regain the necessitation rule. We can apply whenever we want. Of course, phi must be a theorem. So, okay, or a hypothesis. We have a hypothesis, we can apply the necessitation rule as we want.
Okay, I got it. Thank you. So, any other question?
Bruno, your first question was responded in the example.
Maybe it's just some silly points for me to understand. I will talk to you later. Okay. So, okay. Thank you very much, Edson. It was a really nice beginning of the season.
Thank you.